Hello again. Welcome to the Good Systems Speaker Series. Thank you so much for joining us this afternoon. It's good to see many familiar faces. And also, if this is your first Good Systems Speaker Series event, welcome. Good Systems is the Ethical AI Research Grand Challenge here at the University of Texas at Austin, connecting more than 120 researchers across more than 30 disciplines to focus on embedding ethics in AI. Our speaker series brings together diverse perspectives on ethical AI, and today we're really excited to host Dr. Julie Shah. And without further ado, I'm going to introduce you to our host for today, Professor Justin Hart, who's a professor of practice in the Department of Computer Science here at the University of Texas, and also co-leads our Good Systems Living and Working with Robots research project. Professor Hart, I'll turn it over to you.
Cool, thanks so much. So just by way of, what happened? Oh, okay. Oh no. Oh, okay. Sorry, the Zoom thing just changed on me. I'm just going to introduce Julie. I'm going to turn it over to her. So Julie Shah is the N.H. Slater Professor of Aeronautics and Astronautics, Faculty Director of MIT's Industrial Performance Center, and the director of the Interactive Robotics Group, which aims to imagine the future of work by designing collaborative robot teammates that enhance human capability. So Julie, I'll go ahead and turn it over to you.
Hello, thank you so much for having me. I'm delighted to be here. Let me go ahead and share screen from my slides. All right, how does that look?
Looks good. We can see it perfectly.
Wonderful. So hi there, I'm Julie Shah. I'm faculty in Aero-Astro at MIT. I run an AI and robotics lab, the Interactive Robotics Group. And I also co-lead MIT's Work of the Future initiative. And so I'll talk today about sort of a thought experiment for us to work through and share my and my lab's latest thinking with you on how we may be able to overcome the autonomy paradox with generative AI. So many of you, some of you may be programmers or engineers. So this comic would, I think, resonate with you. He says, I wrote some software that automates one of my mundane and repetitive tasks. Careful, the automation paradox states that the more we automate easy tasks, the more we're left with the difficult task of dealing with the system when it goes awry. I already thought of that and wrote a function that handles any faults, and another one that just watches that one. I've thought of everything. It's foolproof. So what will you do with all of your extra free time? Hold that thought. I'm getting a compiling error. Okay, so for many of us, this is likely a familiar feeling. And it's funny, we're quite used to this. But what I want to do is start by talking about some historical examples and the real world implications of the autonomy paradox. So imagine yourself at work and you're called into a meeting and your organization is rolling out a new technology and it's going to change everything. In fact, it seems the system can basically do your job. And your organization is under great pressure to cut costs, and you're pretty sure that they're happy to do so by cutting jobs. And so it's only a matter of time before you're shown the door. So
sorry. We just saw a black screen there, but now it looks like we see
no,
stuff.
no, that was on purpose so that you could use your imaginations.
All right.
But it's not today. The year was 1982. This New York Times article was from 1984, but in 1982, General Motors announced a factory of the future in Saginaw, Michigan, where they were going to use robots and automation to achieve lights out manufacturing, meaning there'd be essentially no people. So you could literally run the factory with no lights because robots wouldn't need lights. Well, things didn't turn out as expected. The robots famously placed Buick bumpers onto Cadillacs and vice versa. And the robots actually spray painted each other rather than the cars. And pretty soon after, the whole project was abandoned. That's 1982. So next, let's jump forward to 2002, 20 years later. And over those 20 years, technology has advanced significantly. And at this time, the Navy unveiled their plans for the Littoral Combat Ship, which was meant to be a highly autonomous, intelligent naval vessel that would operate with many fewer sailors. But it's also, actually many billions of dollars later, So the LCS, interestingly, was intended to be operated by 45 sailors, and it actually ended up requiring 60 sailors. Those sailors needed higher skill levels. They worked at higher pay grades than those that were required for traditional ships. And actually operating the ship was cognitively harder than a regular ship, leading to burnout and very significant turnover. There are other details in there as well, actually sort of negative training transfer. So those that trained for operating the littoral combat ship actually performed worse when they went back to operating the regular ships. And in its initial vision and incarnation, this project was actually abandoned as well. But interestingly, from about a year ago, we have this headline from the news. It says the littoral combat ships, there's a few of them that actually exist in the world today. But the headline says 20 years later, the Navy says its littoral combat ships are kind of working. The ships are quote unquote on trend to meet requirements. So these are famous examples of what's called the autonomy paradox, which is that automation doesn't eliminate the need for humans, but rather it changes their roles. And it's easy to fall into the trap of what my colleague at MIT, social scientist Ben Armstrong, and I call zero-sum automation. And the issue is that companies often measure success by simply comparing the cost and output of machines with the same for human workers. And the issue is that this approach limits flexibility. It makes it harder to adjust to changing requirements and objectives. And it also underestimates the value that people bring and overlooks the broader potential for automation. So this issue actually follows us into current day. So believe it or not, today, only 1 in 10 manufacturing firms in the US even have a single robot. And it takes a tremendous amount of time, effort, and resources to set up, configure, program these systems. Really, the largest companies are the ones that can make use of it. Small and medium enterprises, which represent like 98%, 97% of all US manufacturers, lag very far behind. So, what I want to do is talk about the way our cross-disciplinary research at MIT shows that we can avoid this sort of zero-sum trap. And it's through what we call positive sum automation. It's where we do more than to design automation to replace people, but we design it so that automation and humans together can increase productivity and flexibility. And so it requires a different approach to technology development. That's what my lab works on, and primarily what I'll talk about today. But it also requires different approaches to designing for skills and training, organizational change, role reconfiguration, and rethinking how to make the business case for the technology. And my colleagues on our research team will often speak to those points. I'll touch on them briefly today. So one question that I think is really interesting with regard to generative AI is to ask, is generative AI the way or a way to overcome this autonomy paradox? And by that, I mean, can it be a way to increase flexibility and overcome these issues that we've historically seen? So I want to be able to address this question. But before I dive into it, I want to complicate the question a bit further. So flexibility isn't the only goal that we care about here. AI, it's increasingly being deployed in high stakes environments. So we're grappling with challenges and new regulation, for example, of AI in healthcare. AI is even being deployed as a part of the US services. Autonomous aircraft are teaming with piloted aircraft in combat settings. And it's actually a stated requirement of these programs that the AI be implemented in a way that enables, quote unquote, appropriate levels of human judgment. So the question is, how do we know if we've succeeded in enabling appropriate levels of human judgment? How is that measured? What does it mean? So we know from the implementation of prior forms of automation that the use of automation can result in serious negative consequences. It can undermine an operator's ability to identify a problem and appropriately intervene. Humans, even well-trained experts like pilots, can easily become complacent in the technology and overtrust it. It can undermine a person's understanding of their progress through a task or understanding of their environment, their situational awareness. And automation can even degrade manual skills. So that's why pilots, to remain current with their pilot's license, actually themselves have to perform a certain number of takeoffs and landings, not using automation, even though the vast majority of a commercial airliner's flight is typically flown by automation. So even with traditional and more transparent forms of automation, we know, again, historically, that it's very difficult to get this right out of the gate. So I'm showing you here a 10-year moving average of fatal accident rates by Airbus aircraft generation. And you can see with each new generation of aircraft, which included upgrades to cockpit automation, among other technologies, we would see accident rates spike while the human systems integrations issues were being worked out. So, but we can also see that by pushing past these spikes and implementing the best practices of human automation interaction and systems integration, that's actually what's helped us achieve the current unprecedented level of safety that we have for commercial aviation. So when you push out these spikes, we see a much better sort of plateau of this accident rate than we did many decades ago. So the question is, what are these best practices and what lessons can we translate in terms of how they can relate to our new implementations and use of generative AI? So what do we do to, in current day, achieve like what we would characterize as unprecedented success with use of new technologies? And how can we step around these sort of spikes where things can go terribly wrong? So one concept from human factors that's particularly relevant to AI is this concept of situational awareness. It's been widely applied in aviation to address pilots' informational needs, as well as in a variety of other high workload, high stakes contexts, such as autonomous driving, medical care, military operations, search and rescue. And it's been shown to correlate with team performance across all of these domains. So a core finding is that loss of situational awareness while operating highly autonomous systems has accounted for hundreds of deaths in commercial and general aviation. So situational awareness is the ability to perceive, comprehend, and project the state of an environment. And people have to maintain their situational awareness in order to effectively take control of a job performed by an autonomous machine in the event that something goes wrong. So when a person doesn't know what the machine is doing, as it relates to automation, we sometimes refer to this as automation surprise. So the concept of situational awareness has been formalized within the human factors literature by following a 3-level definition. So the first level is your awareness of perception of the elements and attributes in an environment defined within a volume of space and time. The second is taking those observations or perceptions and putting them together to comprehend their meaning. And then third is being able to project their status into the near future. So a person needs information at all of these 3 levels in order to help them perform their tasks effectively within a given context. So as a quick and simple example of what this might look like for a pilot flying an aircraft, let's say we have a pilot who's trying to determine whether they have enough fuel to get to a given destination. Then at level 1, the pilot needs to perceive the current fuel level. At level 2, they need to comprehend what this means in terms of possible range of the aircraft, how much further they can fly with that amount of fuel. And at level 3, they need to be able to project out whether they'll reach their destination before running out of fuel. So at current speed and trajectory, is the destination reachable, considering like cruise altitude, payload, airspeed, et cetera. So that's a simple example for a single task. But overall, a person's situational awareness includes all of the information they need to complete their given tasks. And so this includes information about the environment, their human team members, their status of their task, and also any AI systems or automation that they're working with. So explainable AI is very relevant in this context, and it's addressing the subset of situational awareness that includes the AI system or the autonomous teammate-specific information. And so that's what we're focusing on here. So focusing on this aspect of essay and using the essay framework as a launching point, my PhD student, Dr. Lindsay, former PhD student, Dr. Lindsay Sandeman, and I developed what we call the Situational Awareness Framework for Explainable AI, or SAFE AI. And this is a framework that enables us to systematically determine what information an AI system needs in order to explain about itself in order to support humans in their task. So SAFE AI, much like the Situational Awareness Framework, is a 3-level framework. And at level 1, we're looking at XAI, Explainable AI for Perception, defined as the explanations of what an AI system did or is doing, or the decisions or outputs made by the system. So these level 1 explanations answer what questions and typically give information about the system's inputs and outputs. Level 2 XAI for comprehension looks at explanations of why an AI system acts in a certain way or makes a particular decision and what that means in terms of the system's goals. So level 2 explanations are looking at why and how questions. They typically give information about the system's model or internal decision-making processes or causality as they may be incorporated into the AI system. And finally, level 3 XAI for projection includes explanations of what an AI system will do next, what it would do in a similar scenario, or what would be required for an alternate outcome. So level 3 is answering what-if questions. And it's typically incorporating counterfactual or simulated information in order to be able to provide those details about the system's future behavior in the presence of changes or perturbations to its inputs, outputs, or models. So, relevant here are the what, why, how, and what if questions. Obviously, these very much depend on the context, the task, the human's role, the human's expertise, among other things. So now let's go back to our question. And hopefully I've convinced you that sort of explainability and transparency is really paramount to effective integration of automation and AI. So the question that I want to delve into is whether generative AI is the way to increase flexibility and transparency so that we can overcome the autonomy paradox. So what I want to do is use robotics as an illustrative example in aiming to answer this question as to whether Gen AI can sort of deliver on flexibility and transparency. And this is relevant in many real-world settings because we can think about this question another way. So can generative AI help us essentially like leapfrog past the previous challenges of prior forms of automation in AI, the need for expertise, time, resources, and the ways in which these technologies were really too inflexible? And can it also be implemented in a way that's transparent so that we can support human situational awareness? So the nice thing about running Robotics Lab is that robotics is very visual, as you all know. So let's look at these contexts in relation to robotics applications. And so I'll start with a video that I think we're all quite familiar with, the Code as Policies work out from Google. And this is like an incredibly exciting time to be doing robotics because if you just look at what this capability now affords us, we have a lot, what seems to be a lot of flexibility in specifying objectives for these systems and then the capability to execute them. So we're seeing like put the blocks in a horizontal line near the top, move the sky colored block in between the red block and the second block from the left, put the apple and the Coke in their corresponding bins, etc. And so the way this system is working is that given a functional API, the LLM is learning how to combine API calls to solve novel tasks and how to compose new API calls to solve more complex tasks. So, a key aspect to note here is that these methods are assuming primitives that the LLM can sequence to solve a multi-step task. And then the question is, where do these skills come from? Additionally, the grounding is happening at the skill level, and that might be too coarse to be reactive to perturbation, for example. So if you don't have a reactive strategy within that API to detect that you've dropped an object as you're picking it up, like that's it, right? So you're going to end up with actually an inflexible system at the end due to the whatever granularity of specification you have in your API. So I think there's another question here in terms of the sort of the concern about inflexibility, which is what happens when something goes wrong. So for example, what is the LLM's interpretation of sky colored? Like, what is that grounded to? Or put the apples and the Coke in the corresponding bins? Who decides which bins? What if it's wrong? And so this is not, even though it's natural language, it's not really transparent in the way that we require it in terms of an SAA framework. Specifically, we don't have insights into the features, model details, or the what if scenarios. Okay, it's also fun to look at the other exciting developments in the field around teleoperation and human imitation. So we're seeing, through teleoperation paradigms or imitation learning paradigms, for example, very complex humanoid robots, also low cost robots doing like very challenging tasks, like NIST board tasks are quite challenging. So these are really impressive demonstrations of human imitation for multi-step long horizon tasks. However, for those that do robotics, you can imagine or know the detailed level, the challenge of a system that sort of blindly imitates emotion without developing a deeper understanding for what task success means. And we all have these blooper reels. So, just to look at the blooper reels from Aloha, just as the ability to sort of pause on it and understand, the fundamental limitations of imitation learning, is that when something in the execution is a bit off due to internal errors or changes in the environment, you see the robot pouring liquid on the table, for example, instead of into the bowl. So that's because what the robot sees from the human is that they reach towards the white bowl and then pour. But what the intent is for the robot to reach the white bowl while keeping the pan in the hand. And then if the pan is above the bowl, pour, and while keeping the pan in the hand is a constraint. If the pan is above the bowl is a precondition. But these are very difficult to extract from a continuous demonstration. They're essentially implicit in that continuous demonstration. So on one hand, a robot that learns to imitate a human is, transparent in one sense because their capability is aiming to mirror what a human does. But we can see that the system is still relatively inflexible with regard to changes in the requirements of the task. So what I'm going to introduce is an alternate human-in-the-loop approach to incorporating LLMs so that it adheres to the Safe AI framework and can potentially deliver on both flexibility and transparency. So the key idea is to leverage LLMs to produce the high-level plans that essentially fill in the gaps of the human demonstration. And I'll show you we can do this in a way that's both flexible and transparent. And thereby, according to the Safe AI design guidance, supporting appropriate levels of human judgment. So just to give you a before and after, for the goal of picking up this can and putting it into a bin, without the LLM-based replanning, I'll show you. You see when the robot loses its grasp on the object, so you don't have the recovery that you would require to be able to pick it up and still finish out the task. But with the LLM-based replanning, which I'll walk through, we do see sort of much better performance in terms of being able to handle and recover from those types of errors. So the way this works is we leverage LLMs through an LLM-enabled explanation-based learning framework. We leverage LLMs at 3 levels. So the first level is to be able to query the LLM to propose feature selection. So LLM visual system is queried, and what we are provided back with is a set of features that are relevant to this environment. So you can see information regarding the right end effector position, the center of the end effector, where the can is, XYZ, where the table is, where the milk bin is, where the cereal bin is, where the bread bin is, etc. Those outputs are used concurrently with a task description provided in natural language to down select the set of features that are relevant to this task. And then those are used in learning a classifier for what sort of behavioral mode the system is in while it's executing its task. And I'll come back to that in just a moment. The second level at which we use an LLM is to propose information about the transitions in the behavior and the modal behavior of the robot to be able to encode feasibility of mode transitions. So for example, in the simple example of picking up a can and moving it, you have reach towards the can, you have grasp, and you have transport. So the LLM is queried to provide this transition matrix, first to hypothesize the number of modes and the names required in the task, and then to fill in this matrix of allowable transitions. And essentially, this matrix here is indicating that you can reach and grasp, you can reach, but you can't transport unless you've successfully grasped. Then the third way in which we leverage LLMs is to be able to initialize and learn the constraints of the behavioral modes via counterfactual perturbation or in simulations of these what-if scenarios. So sort of a constraint representation of the allowable modal behaviors of reach, grasp, and transport. And in conjunction with that, there's sort of allowable transitions. So if you don't successfully grasp, you're going to need to go back to reaching to be able to pick up. You can't continue on to transport until you've succeeded according to this feasibility transition. And through perturbation and simulation, the system is developing sort of an inner approximation of this constraint representation of the allowable behavior modes. So you're not looking to imitate only the particular motion that you saw, but through perturbation and exploration, sort of bound the allowable behavior around sort of the particular small number of demonstrations that you received. Okay, so this is the high-level idea of three ways we're leveraging LLMs. And what I want to do now is recall the Safe AI framework. The level 1 XAI for perception, level 2 XAI for comprehension, and level 3 for these sort of what if or counterfactual investigations to be able to predict the future behavior. So what we're doing is actually implementing and integrating the LLM at each of these XAI levels to reduce the burden of producing structured information so that the produced information is human understandable, inspectable, and modifiable if needed. So to map this back, to give a concrete sense of the output, we're using the 3-level LLM. We're using the LLM at these 3 levels so that the output of the LLM is structured information regarding the perceptual elements that ought to be used in developing the representation of the modal behavior of the system. We're using the LLM at the second level to be able to produce the constraint-based logical representation of transition between modes, like what are the steps necessary to complete the task and what are their relationships in terms of task success. And then at the third level to conduct this counterfactual perturbation inquiry as to how the system is allowed to behave or must behave in the case of perturbations. So the benefit here is that there's sort of no end-to-end use of the LLM to robot behavior. At each level, we have a representation that's inspectable, modifiable, human understandable. And then we use those outputs as a part of trusted methods to produce potentially reliable and also verifiable robot behavior. So I won't go into too much technical detail here, but just to spend one more minute on it. sort of visually, what's happening here is we're taking successful demonstrations of completing the task and learning associated with the observation space that is hypothesized by the LLM, the set of classifiers that can classify whether the system is in mode X, Y, or Z. So reach, grasp, transport. The system uses those classifiers in conjunction with that feasibility matrix to be able to score the feasibility of an entire end-to-end trajectory, including trajectories with perturbations. And the utility of these learned classifiers is in both developing sort of an explanation or scoring of why some perturbed trajectories fail, and why some perturbed trajectories are still successful in relation to the modal behavior that you'd expect from the system. And then the feasibility matrix is also used for replanning. So if the system is perturbed, it follows the allowable transitions to be able to retry and ultimately aim to complete the task. And the key detail here is that this whole framework is fully differentiable, allowing for back propagation for learning. Okay, and so there's, as I mentioned, there's sort of many inspectable outputs of this system. And just to illustrate one here, imitation with LLM-based planning, here we have the ground truth annotation of the different modal behaviors of the robot, reach, grasp, and transport. And we're able to show that we're able to ground and recover those three modes segmented quite closely to the ground truth. So it's a good indication that we're learning a high quality model here. So what I want to do is show you what this enables sort of put together in an even more interesting task. So here what we're doing is we're teaching the robot with one or very few demonstrations through kinesthetic teaching to pick, scoop the marbles and dump them into another bowl. And so you can see here what's represented are the in-distribution states. And through this framework, we're able to see success under arbitrary perturbation as a part of this process. So for example, when it's perturbed such that it drops all the marbles, it uses the LLM-based replanning to re-scoop and ultimately succeed in finishing the task. And so this requires reactivity and replanning both at the motion level and at the task level, and in a way that the motion level and task level replanning is consistent with the criteria for success of the task. So a few more highlights of this approach. So using the observation space of the robot and the LLM hypothesized features or attributes that are important at level 1, we can see the benefit of this in, in prior versions of this demo, we would hard code, what to look for in the sensor space to indicate that marbles were in the spoon. We can see here that we're able to learn rather than hard code this grounding classifier, as well as use it in a way that allows for this, this successful replanning in the face of perturbation. And then lastly, just to highlight the what if or counterfactual aspect of this approach, we can, here the success criteria for this robot is to move through the different phases visually indicated by colors. So move through green, blue, yellow, and then red. So if you're perturbed out, you want to loop back and start with green. We can learn through self-supervised data generation. For example, just let the robot run for a few hours, moving through this space, but scoring the end success of each of the trajectories. And we see that the system can ultimately recover the constraint relationship of the different modes, as well as the appropriate recovery behavior. So when the system is perturbed, it is able to go back and then restart in the green to aim to continue along the trajectory. So we've had, we conducted sort of larger scale experiments with many people coming into the lab. and interacting with the system however it is they wanted to. Some were adversarial, some were cooperative. It's fascinating to watch all the different ways that people, uninstructed, will interact with the robot. And then just to give you sort of one pull out here, you can see this person, as the system went to scoop the marbles, went and disrupted it, and the system went back to rescoop. It's actually refining, it's modulating its policy in response to that error. So you see it recognized that its second error was that it scooped, but it didn't capture marbles. In this case, the system, even under perturbation, is able to better maintain, through online updating of the control policy, the correct orientation to be able to ultimately drop the marbles into the bowl. So this is a lab experiment and investigation, but I will say that I'm personally feeling quite excited and positive about the ways that we can think about architecting the new capabilities we have in generative AI into robotics, specifically with the goal of increasing flexibility and transparency. And I do believe that there is really great potential here to help leapfrog the challenges that we've seen with traditional forms of automation and AI. And maybe we can use this as a technology that does not continue to doom us to this autonomy paradox. So that's the view from an AI and robotics lab. And to finish out, I also wear a hat at MIT as faculty director of the Industrial Performance Center. In which it's a longstanding center at MIT that has a history of setting up novel academic industry partnerships, specifically to be able to gain and share on-the-ground information as to what's happening beyond the lab in an industry, and also specifically with the mandate to study the new ways that technologies can result in better jobs. And so, for example, as a part of IPC's research portfolio, we look at industrial automation and robotics in manufacturing. We look at software automation in healthcare, and we look at design and implementation of those technologies, but also through cross-disciplinary collaboration with social scientists and those from our Sloan Management School. We also look at organizational and management decisions that can help us to realize new technologies that can go hand in hand with better jobs. And for me, like a really interesting aspect of doing this research with my colleagues from other disciplines is that as a technologist, you see the question that I ask, like, how can Gen AI help us leapfrog? How can we design a technology in a way that can sort of change the equation? But there's really interesting study of, given a technology, what is the effect of sort of all these other organizational and business decisions? And so, for example, overcoming the autonomy paradox. And so to illustrate this, I want to share the way we do research is through case study often. And we write up case studies, but we've also recently begun developing short documentaries of some of the case studies to be able to share our findings with a broader audience beyond the academic audience. And so I want to look at a case study of a small medium manufacturer in Ohio, G&T. And what's really interesting about them is that they're using off-the-shelf industrial robots and automation equipment, but the same equipment that many other manufacturers really struggle with making use of and getting it to work. So it's just a few minutes long. I'll play this sort of video documentary and then kind of come back to the larger lessons behind the ways we can try to address the challenges we see beyond new technologies.
Now turn the robot on. I mean, these are new, but if you ever watch the original Terminator movie, at the end, they're using machines like this. It's for loading and unloading the parts. It saves us a lot of time.
Everybody sees a robot roll out on the floor, and the first thing everybody thinks of on the shop floor is, well, that's it. They're gonna cut the workforce. Someone still has to monitor, someone has to tend, someone has to set up, someone has to change over that robot. So you still need that skill set. You still need a person.
When you're in a small shop, you got a lot of different things to do. This allows me to run the robot down there. I hand that one and I do the inspection too.
When they're new here, they're like, oh, I can unload and load that machine faster. I'm like, yeah, but you can't unload and load that machine faster 24 hours. You can't do it for 48 hours, and you can't do it for 7 days and work every single hour. So by getting the people trained in the technology like this, you can become very competitive on the global stage. GNC manufacturing was started in the late 70s by my grandfather and my father, Gerald and Tom. They came over from England. Myself. So they built it from having just a few customers to where we are now, manufacturing parts, whether it's for the aerospace industry, food industry, lift truck and heavy industries, and all those items that fit in there in agriculture. And we compete in that global marketplace with robotics, automation, and trying to keep up with the latest technology trend.
Before we got this, I used to load them by hand and it was, I believe, faster. Just kidding. But it actually loads it better. When you're loading a part, I'm holding it like this. I'm not getting equal force on it. It's just my muscles. So each time it's different, you'll get different sizes and you're not going to get that clean surface. So this will do it all for me. Saves me a little work, saves the back.
First push into the robotics for the heavy lifting was a safety concern for our workforce. And then once we did that, our ROI on the first robot we bought for heavy lifting, we had the ROI of $140,000 investment. Took us 3 months because our efficiency went so high on day shift that when we ran it on night shift, we actually gained all that time back, and we actually got so far ahead. We had that many of those parts through the lathe that we could no longer support it with our other processes in the shop. So we had to relook at all the other processes in the shop.
We are so busy. A lot of this is at we have another warehouse, but this is jobs I got to check in, just raw material. So we've been speeding. We got another machine coming to town. So that'll be interesting.
So anybody can go out, purchase exactly what we have. There's no real magic to what we do per se with the equipment. The more of the magic is the culture and the workforce of getting them to accept the value of the automation.
I'm 60. As for a computer, I don't own one. I don't deal with one. So it's not that hard.
The way we had it set up was we had a bonus system that was in place. You just got to hit 80%. Well, there's no way the robot's going to duck down under 90. So these guys are hitting these 10%. So they're hitting these huge bonus markets. And that's what really made it easy to get the robots and automation on our shop floor was everybody wanted to run the automation. Everybody wanted to learn the automation then. We believe in the all ships must rise mentality. So if you don't backfill in the community and develop them into these higher technology, machining and manufacturing jobs, you have nothing to pull from you. So it seems like it's a fairy tale, but then you realize all of a sudden you are actually living in that fairy tale because the production from the automation is actually carrying your shop. And all of a sudden you realize you have a happier workforce and you're making more parts. So you have a bigger ROI. which then allows you to actually pay all of your workers more money because you actually become more profitable because you become more efficient. So if everybody's happy, then we all gain, and then all ships will rise.
So I find this story incredibly inspiring, and I can't stress how unusual this story is, this case is as well. And, I can't help but think, thinking back to GM, thinking back to the Navy, just thinking back to other manufacturers today that are looking to upgrade their technology. Like, if only they could follow Colin's playbook at GNT. They cracked the nut in terms of being able to upgrade their technology, increase their productivity, and through that process, they've grown to offer more and better quality jobs. And again, they're doing this with the same technology that everybody else has. And so, a few takeaways here are that automation that can be flexibly tasked and directed by employees accelerates innovation. And this requires companies to invest in training and build employees' independence in operating and experimenting with this technology. We also see through our research that a bottom-up approach to this is crucial. So employees that are closest to the process also need to be closest to the technology. So GNT successfully implemented this approach, improving their productivity and employee satisfaction. And we have great examples also of this working well in big firms, in large firms. And then we also see that traditional productivity metrics do often fall short in evaluating the success of automation. And that measuring a machine's practical flexibility as well as its enhanced performance and satisfaction, and as well as the enhanced performance and satisfaction of human teams is really crucial. And in this case, the sort of incentive system was very much key, a core part of all three of these approaches at GNT. And so, I think it's really striking that a vision of a fully automated future is not about eliminating humans from this equation, but about incorporating them to make humans more capable and vital in the workplace. So I think what's exciting is, as we're conducting this research on more traditional industrial automation and robotics, and we learn about the effective organizational and management differences that can make all the difference in achieving the sort of win-win-win or positive sum automation. Again, we can ask the question, what can we learn and what can we take forward as companies are beginning to employ generative AI? And to this end, as a part of IPC and Work of the Future, we're also convening a generative AI working group with industry partners, 40 plus large firms across a set of sectors, where they're sharing with us and we're learning from their early use cases of generative AI, so that we can, again, understand what's happening on the ground. And so we're studying a range of applications and use cases across healthcare, financial insurance, real estate, manufacturing, tech, and other sectors, looking at applications related to productivity, decision support, as well as innovation. And so you can find out more about this work at Work of the Future at MIT.edu. With that, I'll go ahead and wrap up, but I want to give you one plug since I'm speaking to many of you in Texas. So this is a request of the organizers of a very unique IEEE conference that's going to be hosted in Austin, Texas in April. This is the inaugural IEEE Life Members Conference. The speakers for this conference include really great people, I think, relevant to your interests, like Rod Brooks, Manuela Veloso, Barbara Gross, many from industry, and NASA. The conference is going to delve into technology related to the future, aging societies, renewable energy and sustainability, applications such as financial, smart systems, infrastructure, it's meant to bring together life members of IEEE along with those at earlier stages of professional development. So I encourage you to consider registering and attending that conference as well. And so with that, I can wrap up and take any questions. Thank you so much.
Yeah, and so those of you who have questions, go ahead and either raise your hand or type them in the chat. Julie, if you just want to look through the chat, there's a bunch of questions from one of our undergraduate students, or we can manage this however you prefer.
Let's see. Yeah, absolutely. Okay, so I see the AI assistant. Hold on, I'm scrolling. Let's see, Tony. What are my questions? Okay, general question. When we continue to automate easy tasks for humans, only the difficult tasks remain, depriving humans of the experience of practicing foundational skills. In this process, is there an essential element of creativity and repetition that increases human ingenuity in solving difficult problems? I'm curious if there are physical processes that AI automation should not replace for human creativity if they exist. So that's a really interesting question. So you can see that phenomena in introduction of cockpit automation and current practices for training and keeping pilots current with their skills. And the discussion comes up in other sectors as well, in law, in healthcare, in the medical field. And so like in the most grounded way, what we know from prior introduction of automation, like in the cockpit, is that you actually, by automating tasks that are easy to automate, in the short term, you actually do undermine a few aspects of an ability of a human to perform and to advance their skills to perform in more complex situations as well. So we do see skill atrophy from just from lack of like practicing, say, manual skills that you would have in flying an aircraft. But in addition to that, in training, you see in aviation, you're required to learn how to fly the aircraft without the technology to build up your most fundamental understanding of how the aircraft works, which is very important if you have a degradation in that autonomy or an error with that automation, to be able to understand at a fundamental level what's happening with the aircraft. Interestingly, with the work that we do with manufacturers, I thought it was very interesting in terms of like CNC programming. They go through a similar process. So as a number of these firms are developing curricula to train their associates to increasingly use automated technologies, these sort of training programs always start at the fundamentals. So like a machinist is required to start from the beginning and gain the fundamental skills associated with machining before handing over aspects of that to automation. And I had wondered about that, if that was really necessary, or what the view on it was. Is that just because that's how machinists have been traditionally trained? And what we've heard is that it's actually fundamental to understand at the lowest level what's happening with the speeds and the materials, and gain those basic skills to be able to effectively use automation as you aim to use it for more complex geometries. So we have a few of the examples where you really don't want to aim for short-term gain in introducing automation at the expense of sort of like longer-term growth in a variety of aspects, in terms of your people, in terms of your ability to do or solve more complex problems. And I think that's one of the issues that we hear currently coming up with the companies we're working with as a part of the generative AI working group. Like, to what extent does changing an HR role fundamentally and taking away sort of the drudgery, or in a call center, taking away kind of like the drudgery of responding to certain types of email inquiries, technical inquiries, actually undermine that workforce's ability to do the sort of more judgment and creative work. Anyway, so that's just to, I think, echo the importance of that question in the past and currently. All right. let's see. Using LLM for robotic control tasks, how can we be confident that interpretation of actions aligns with their intended outcomes rather than just describing them? Is there a guarantee that interpretations and explanations will always correspond? Okay. So this is for safety critical and high stakes applications. This is a really important question. And so unless you're taking a relatively heavy-handed approach to specify the particular structures or representations that you want your system to use, you don't have a guarantee that they're going to correspond. What's worse is that, even in the explainability literature, if you just look at salience methods, for like images, like what makes it a bird, the beak and the wings, or what makes this this image likely to exhibit sort of a cancerous region, and it highlights, it makes salient the set of pixels that are supposed to contribute to that prediction. So we and others have shown that using many of the existing and most popular saliency or explainability methods, the pixels that they highlight or the words that are highlighted in a sentence do not actually correspond to sort of the internal decision making of that classifier or predictor. So so even in the sort of the more trusted methods we have, never mind for LLMs, for explainability and transparency, you really don't have, you have to perform very rigorous empirical investigation to confirm that your explanations are corresponding to the features that are actually being used in that prediction. And I'm happy to refer you to some papers on that. And that, I think, a whole different can of worms is opened with LLMs, because our existing methods for explainability and transparency in many ways fall short with generative AI. And so I'm particularly excited about the ways that you can architect it as a part of a system and produce structured outputs that are directly inspectable and then useful and trusted methods, for control or planning. And that's sort of what I've highlighted here.
So Stacy's saying that we probably have time for one more question before we move into like our little closed discussion. So what I'm going to say is maybe not faculty who will be joining us for the closed session, but maybe one more question other than Tony, because he put like 4 back to back in the chat. Does anyone?
Yeah, you can skip my question. Yeah, you can skip my last question. Thanks for answering.
Thank you. Let's see, I'm hunting for another question here. I see a comment on Tesla.
Yeah.
And, that's another example that sometimes I include in talks or sometimes I don't. But, they, through their process, they also learned the hard way. I think there's like this great quote from Elon Musk that says, like, through this process, I learned that human hands are magic, like, yeah, so that's another example, a more recent example. But if anybody else has another question they'd like to ask, I don't think I see one in the chat. I'm happy to answer it.
Do you want to take Tony's last question then, perhaps? Julie?
Sure, I'm happy to. Okay, let me scroll back up. I understand that using feature selection and task description with LLM facilitates robot behavior and state transition. However, for tasks that are not universal, the accuracy of robot behavior may decrease, the randomness may increase significantly. How is this addressed or explained in explainable AI? Specifically, I'm curious whether explanations are generated regardless of randomness and interpretation, or if they're tailored to align to the level of understanding or perceived limitations. All right, Tony, I'm going to have you ask the question and restate it a little bit for me, because I'm not fully sure I understand it.
Yes. So I can restate my question. Sure. So like a general task the robots did, like moving on apples, would like have lots of data in it, and they use the data to train that. It's all data driven. But for example, like let's say very specific, like Korean heritage, like some kind of pot, some kind of like Japan things. it might be really hard to understand that specific task because it's not well trained about that data. So in that kind of explanation, do you just generate the like a hallucination explanation, or do you like make a limit or boundary that AI cannot explain over that general data testing thing? That was my question.
Okay, yeah, thank you. Okay, so like in the case so let's see. So for a less common object, for example, or at least one that may be underrepresented in the LLM, so the approach that I highlighted here from our lab, it's an approach that I think would be especially relevant to that case, because what we're aiming to do is to be able to automatically ground the language with demonstrations, or ground the demonstration with languages. Ultimately, it propagates both ways. So given a continuous demonstration, given a full set of sensor observations, and then given some priors as elicited through the LLM for features that would be relevant from the visual scene, and then information that would be relevant for understanding like the task flow or the task structure, you're looking to automatically ground that continuous representation in interpretable representations, including like high-level labels for behavioral modes, as well as sort of the constraint representation on what it means for allowable execution within a mode and transitioning between modes. So, for what I presented here, if the LLM doesn't incorporate sort of any information regarding like the sort of like language labels for the novel object, then you have sort of an interactive process to be able to ground that. But often with manipulation of objects, like there's mappings to affordances. So the way you might use like one type of pot like might look similar to other types of pots, and there's ways that you can sort of translate that information by grounding it in related tasks that have similar sort of task structure or modal behavior. And so, yeah, I think it's an interesting question of how you could augment, the LLM, if it lacks that. But like systematic investigation of, what type of task structure that the LLM is particularly good at providing or harder to provide, I think is relatively newer. So in the iClear paper I've referenced here, we essentially show proof of concept in a set of tasks under which the LLM does perform well at identifying the features and providing the task structure. But the question is like, well, what are the set of tasks in which it's going to reliably work well? And then when it doesn't, what is the role of the person to fix it up? I think what's encouraging to me is that the output of this process is still a human, inspectable, and understandable representation, and a person can directly fix that representation and continue with the next steps in the pipeline. And I think that's a particularly promising way in which to engage a person, sort of iterating on semantically meaningful, structured representations for use with trusted methods.
Thank you for responding. Thanks for the lecture too.
Thank you.
All right, so I think we're coming to the close of this part. If we can all thank Julie again, real quick, and then folks who are on the Good Systems.
Thank you,
faculty,
Julie.
staff,
Thank you so much to everyone for attending today. And we'll look forward to seeing you all at the next Good Systems Speaker Series event on April 3rd, featuring Dr. Howard Besser from NYU. Thank you all.